A very warm welcome to the new episode of Ink and Insights. This is your host, Sumit Sharma Samir. This is a Nepal-based podcast, and if you are interested in listening to the thought leaders from around the world, please subscribe to my channel. I'm extremely pleased to welcome Nobel Laureate Professor Dr. Reinhard Genzel in my program today. Professor Genzel is a distinguished German astrophysicist, renowned for his groundbreaking research on supermassive black holes and galaxy formation. Born on 1952 in Bad Homburg, Germany, Professor Genzel is a director and scientific member at the Max Planck Institute for Extraterrestrial Physics since 1996 and has significantly advanced our understanding of the universe's most enigmatic phenomena. Throughout his career, Genzel has received numerous accolades. He was awarded Nobel Prize in Physics in 2020, Crawford Prize in Astronomy by the Royal Swedish Academy of Sciences in 2012, and Saw Prize in Astronomy in 2008 for his significant contribution to the field of astronomy. Sir Genzel, it's such an huge honor to have you in my platform. Thank you so much for your time, and welcome to the Ink and Insights with Sumit Sharma Shamir.
Okay, I'm happy to be there.
Sir, it would be very interesting to understand what initially drew you to astrophysics and how has your passion evolved over a period of time?
Mm-hmm. Well, I have so to speak, an inheritance problem in that my father was already a physicist. And so he, early on, he was a professor in Freiburg University. And so he early on excited me to do experiments. Now, actually, at that time, when I was maybe 15 years old, I wanted to become an archaeologist. And that was really what I really wanted to do. And but then, as I was reading about archaeology, I noticed, well, okay, the Greeks are done, the Romans have been obviously well researched. The Egyptians too. India is known well. So I realized what's left really, and then realized that maybe the only thing which was left was the jungle in at the equator, and so I'm scared of snakes. You see. Yeah, well, so anyhow, but then actually the path toward physics was clear, but initially actually what I was doing in school, other than being in school, is that I was very, very eagerly doing sports, and I was at that time when I was 15, 16, 17 years old, trying to participate in the Olympic Games in Munich and become one of the team. I did become one of the team, and I was, as a young person, Germany's best for a year, best javelin thrower. But then you see, at some point you have to decide. And so I made that decision, and I decided for physics. Now, physics is a large field, of course, and so you study the undergraduate years, and then, of course, question is what kind of physics. And again, my father, acted as a mentor and said, well, particle physics, lots of people wouldn't advise that. Nuclear physics is really a field which has been, now coming to a sort of not an end, but not as interesting anymore. Solid state physics, no way you go there because I'm there. And and then he said, well, my mother always wanted me to do astronomy. And we now have in the Max Planck Society, by that time he was actually a director of the Max Planck Society, and he said my mother already felt astronomy is a good field, and we have a new institute for radio astronomy in Bonn. Why don't you check that out? So that's how it happened.
Right. Very interesting. Lots of, deviations and finally to the astrophysics. Your work on black holes has been revolutionary. Can you walk us through your most significant findings?
Well, so I've explained to you that I started in what one calls radio astronomy. So that's a long wavelength, and these long wavelengths, there are certain techniques which one can do there, which you cannot do in the optical. In the optical, as most people assume, you have a big telescope, and then you look through the telescope, and then whatever you see, you see. In radio waves, what you can do is you cannot use only one telescope, but you could use a whole bunch of them and connect them up electronically to what we call an interferometer. So you combine the if you like, the radio light and interfere it and form a equivalent telescope of the separation with the resolution of the separation of the telescopes rather than only the resolution of a single telescope. So I'm saying this to you because in the end, that turned out to be one of the key breakthroughs after what is really a 40-year journey, I have to say, in this field. Now, the issue of black holes is an old one, honestly. It already was mentioned in the 18th century, believe it or not, but then definitely in the theory of general relativity by Einstein 109 years ago. And the idea is pretty obvious. Let me try to explain that to you. The idea is pretty obvious because it clear through various experiments and that the fastest communication in the universe is light, despite what science fiction movies will tell you. The fastest communication is speed of light. And so that's number one. Number two, you have to know is, according to the theory of general relativity, also light sees gravity. So that's very different from what Newton would say. So let me give you an example. If you have a star, well, let's take the sun, and you look at the sun, and there's a star behind the sun, just looking, across it on the side. Then, according to Newton, the light rays from that distant star would just go straight at us. While general relativity would say, no, that's not quite right. It's actually the light is bent due to the effect of sees gravity. And now you take these things together with the already known fact from Newton's theory that when you have a mass like our Earth or the Sun, and you try to move away from it, then you have to have a lot of energy. Okay, let's think of a rocket. You would have to give that rocket a certain speed, and that speed is characteristically dependent on the mass of the object, but also on the size. It's the ratio of the mass and the size. So the more massive and the smaller an object is, the faster the rocket has to fly in order to get away. And so now you can, in your thoughts, I should say for the sun, that experiment would give you a speed of the rocket of 600 kilometers per second. On Earth, it's 11 kilometers per second. Something which we do all the time now. But now imagine a sun, same mass, but instead of its real size now, shrink it to 3 kilometers. Wow. Then, while the mass is the same, the size is smaller, and so that the escape speed is correspondingly larger. How large? Well, in this experiment, in my mind, so to speak, in our minds, the speed is the speed of light. Oops, there we go. There's a problem. Make it a millimeter smaller, and the speed would have to be bigger than speed of light. And so that's not possible. So if you had such an object, then anything inside of a characteristic radius, which is called the event horizon, cannot communicate with the outside, neither through sending a rocket out nor through light. Okay, there you go. Now we know what a black hole is. But that's a theoretical concept. The question is, do these things really exist? And that took a long time. And only in the 1960s did people begin to actually see far enough away that you could see objects which might be conceptually be massive objects of millions or even billions of solar masses, which are a black hole. But as you know, in science, it's not like science fiction. If somebody says, I have a black hole here, that doesn't mean anything. unless you can prove it. It's not politics. It's science. And so to prove it, what do we do to prove it? You can't see it, right? We just discussed that. Right. And the answer is, the way to see a black hole is you look at what's around it. And what is affected by its gravity. So that could be gas clouds, or that could be stars, or whatever. And then you measure the motions of these gas clouds, very, very much like in the solar system. Because the sun is there, the planets move on certain orbits. And the innermost planets move faster than the outermost planets. Remember, the Keplerian law is that, the speed is 1 over the square root of distance from the sun. So that is the kind of proof we are using. We're using test particles to measure what, mathematically is called the curvature of space-time. And that is, so to speak, the technique. And the problem is, these damn black holes are so small. They are really massive, absolutely. Millions in the center, 4 million in the center of our galaxy, which is the nearest galaxy, and distant objects up to 1,000 billion. 10 billion, and so they are obviously very massive, but to become a black hole, you're really very, very small. I mean, the black hole in the center of our galaxy, we now know, has a size equivalent to an angle of about, a few centimeters on the moon.
Wow. Despite that, the concept of black holes has fascinated both scientists and the general public. Why do you think they capture our imagination so profoundly?
Yeah, no, I think that's a very good observation. My answer to this is, of course, it's the mysterious part, but it's also the curiosity. And in a way, astronomy sort of touches on things in human beings which have to do with a basic curiosity. Yeah, what are these things which are up there radiating, these stars? Why are they there? What made them, and all of this. And then you come to these things which you can't even imagine what they are. We have not talked about the fact that the theory of general relativity also says not only is there an event horizon, but also all of the energy mass of the object is in the center in a point. And that means in a infinitely density region. Absolutely absurd. How can that be? So this is this sort of, we don't understand. We would like to understand. And you're quite right. When I give public talks, even if, or especially children of 7 to 10, wow, they sit there mesmerized by this concept. And the good thing in astronomy is we have pictures and we can show movies and so forth, and we don't have to hide everything behind a very complicated set of mathematics, which makes it very difficult to get there. So, well, no, it's wonderful. In that respect, I believe we are a messenger of science to the public, and that's very important because we need the support of the public to understand us, and we need science to understand the universe. But let's be clear, out of this also comes technology. And of course, many people say, well, look, you guys are pretty bright people, but, these stars, they will still be there in 3,000 years, okay? So why don't you, stop what you're doing with these stars and black holes. Instead, take your obvious, your intelligence, take it and invent stuff which is good for human mankind. Well, I could go through with you through some of the most fundamental technologies which we have and we are using today, and we will find that they were invented not just for the technology and not for the technology per se, but because someone was curious about something else, about a scientific subject, and then on the way found the technology, and that then could be used. So I argue that our job is to excite, our brethren, our population, to be interested in basic research, because number one, we understand more about the world and the universe, and number two, because it does in the end lead to technology.
धेरै टाइम छैन है, बिहे गर्नु छ भने गरिहाल, नत्र घरबाट मलाई अन्त्य बिहे गर्दिनु।
भर्खर 3 वर्ष भयो एमबीबीएस जोइन गरेको, 5 वर्षको कोर्स हो। के भो? अचम्म छ। एक्सक्यूज मी सर, मेरो 5 वर्षको कोर्स 3 वर्षमा सकाउन मिल्दैन?
गेट आउट।
हेलो,
के सोच्यौ त?
के सोच्ने? मैले प्रिन्सिपलसँग पनि कुरा गरिसके। 3 वर्षमा पनि के हुन्छ? के हुन्छ 3 वर्षमा?
के भयो भाइ? ल बस। साउजी, एक कप चिया। कसले भन्यो 3 वर्षमा केही हुँदैन भनेर? यो हेर, एलआईसी नेपालको धनवृष्टि योजनामा 3 वर्षमा पैसा फिर्ता हुन्छ।
ए हो र?
जीवन बीमाको साथमा धनवृष्टि 3 वर्षमा एलआईसी नेपालको धनवृष्टि योजना। एलआईसी नेपाल।
Warm services to delight your senses, taking hospitality to newer heights. Nepal Airlines.
Right. And Professor, do you agree, to some of the claims that say that, the black holes could be portals to other dimensions? What is your perspective on such ideas?
Yeah, okay, so there is, in the normal solutions of Einstein's theory to the problem which I have sketched out for you, that is not the case. Okay, there's just a single object which has this event horizon, and once you're inside of the event horizon, there's absolutely no way to escape falling in all the way to the center where all of the mass energy of the object is. No more escape. But mathematically, you can construct a mathematical solution called a wormhole, where, so to speak, you form a connection to another black hole and do good screwing together of these two connectors, and then you could go out the other way. I would say most physicists would say this is not a very real solution, because when you look at the mathematics of the problem, is if you had such a careful construction of a wormhole, you cannot transport any material through it. So, in other words, you can maybe sort of think of it as an object, but you cannot let in something fly through and they'll come out the other way, because then this throat will collapse. So it's a mathematical construct for all I know.
Right. And what are some of the most pressing issues in astrophysics today that are unanswered?
Well, I mean, the first and foremost, of course, we would like to understand the universe as a whole. How did it come about? We understand now that there was a very special moment, 13.776 billion years ago, when the universe was extremely hot and compact. Not like a point. You should look at this as sort of a spatial concentration, but a lot of energy, and then it exploded in an expansion. And that expansion is ongoing. We can measure it. You would have thought that if there was a finite amount of energy in this explosion, and you work against gravity, then the explosion should slow down. But it doesn't. So that's a riddle we don't understand. Okay, if you look at the physicist's description of it, you will find the word dark energy, but we don't know what that dark energy is. So it's basically a short for we don't know what it is, but we can see it. We can measure it pretty accurately. Another thing is if you look at the bits and pieces of the universe which we can see. Our Earth, us, the Sun, galaxies, the many suns, and other galaxies, and you add up the masses of all these objects, you end up with only a few percent of the total mass which must be in the universe.
Wow.
Oops, how is that possible? Well, it looks as if there's another form of material which you only see through gravity, but doesn't radiate, and we call that dark matter, if you like, and so we would like to understand what it is. Is it a real particle? Can we measure it in the lab? Or what is it? And we haven't found a solution yet. People are really working very hard on it, and it's a problem which I would say we have a lot of indications on it, because we can measure how fast things move in the cosmos at large distances, and thereby get a sort of a feeling how much mass there might be, and we can speculate on whether it's an elementary particle or whatever. So there's a lot. I'm very confident we will learn, and maybe even see in our laboratory these dark matter particles. Dark energy, I'm not so sure. So that's the universe at large. Then let's come to the bits and pieces. Us, stars, galaxies, and also black holes. There, the question is, how did they form, and when, and how did they grow, and how is there an end to this growth, and all of this, and the amount of knowledge which we have gained over the last, say, 20, 30 years is enormous. I mean, astronomy is an old discipline, right? Thousands of years.
Exactly.
Indians, people in Mesopotamia, the Greeks, the Chinese, everyone did astronomy before physics, but we're not done yet. And right now, it's one of the most active fields. It's fascinating.
Exactly.
Yeah.
It's so interesting. I mean, and what impact do you think, discovery in astrophysics would have on humanity's broader understanding of existence?
Well, I mean, okay. I mean, there are questions which we cannot answer. I told you some, right? What is this dark matter thing? What is this dark energy thing? So there are many experiments currently running to try to get insights on that. Then there come questions which I should say we cannot touch. And one is the issue of what is in the center of a black hole. And the answer is very clear. Suppose you and I get into a rocket and fly inwards to the black hole. It's not that this event horizon is a wall where we, boom, and then that's the end of it. No, in principle, if we are stable enough, we can fly through the event horizon. We will reach speed of light, and then, well, we fly to the center, and we cannot stop. We cannot turn around. And if we then, make nice pictures and stuff like that, and begin to understand what's inside the black hole, I'm sorry, we cannot write a paper and send it to Nature and get a Nobel Prize. It's not possible.
We'll keep flying then, Professor.
So that's one of the things that this is an impossible experiment by definition. Frustrating, isn't it? There's another sort of frustrating thing. Suppose we build two black holes of the same mass, and in one of the black holes we pile Himalaya rocks, all in there, and in the other one we pile rocks from the Alps. In Europe, and then at the end we ask ourselves, can we see the difference between these two? And the answer is no. Yeah, they have to. I mean, if the mass is the same, it can't tell the difference. Well, there are many quantum physicists many colleagues of mine who would say absolutely you can tell the difference, because there are some characteristic quantum features which may be difference between the Alps and the Himalayas. And so those you should see. So that is called the information paradox. Another, thing we just don't understand. And then finally, of course, if you wish, is the greatest riddle of all is what was before the Big Bang. Yeah, I mean, it's clear. Many people want to know this. And my answer to this is, look, I'm a simple experimentalist. I can research what I can find something out about, but there I can't. So I'm sorry, I'm too dumb for this. I cannot.
That's a huge question, Professor. Given the rapid growth in observational technology, where do you see astrophysics in the next 2 decades or so?
Yeah, well, I mean, I told you I was, last week I was in South America. I did so because I'm often in South America, because that's where we are working with the telescopes of the European Southern Observatory in the Atacama Desert of Chile. But the reason I was there is to accompany our president of Germany, because he wanted to see that. See, I mean, the politicians are quite eager. And I wanted to show him, and he was really excited to see our new telescope in the making. It's not ready yet. The normal telescopes, big telescopes in optical astronomy are up to 10 meters in diameter. As I told you, one can combine them, like in radio astronomy now. That's the technique which we have invented to an interferometer and thereby get high resolution. But the dream, of course, of a still bigger telescope is there, and we're building it in Chile, right next to the other telescope, and it has a diameter of 40 meters. A gigantic thing. 40 meters, that means, The whole structure is about 100 meters across and 100 meters high. I mean, this is like a cathedral. It's just absolutely fantastic. So this is what what we want to do. The interferometry we want to improve on. Obviously, it would be wonderful to also do more in space. And undoubtedly, there will be more in space. But now we come to a problem for all of us. And that's not only astronomy, but it's also physics. And that is cost.
Right.
Unfortunately, and understandably, as you make these things bigger, even if you have better technology, they come to a point when the costs for these machines are getting so high that even the most supportive politicians and societies say, "Oops, sorry, we cannot." Yeah. Well, what you can still do, and that's what we do, is to collaborate internationally, and that's a good thing. That's a good thing because, of course, international collaboration, by definition, prevents wars.
Exactly.
and as you know,
that's what we need at this point of time.
That's what we need right now. It looks like we are 100 years in the past again, and we don't want to happen what happened then. So anyhow, international collaboration gets you further by some more, but there is a limit. And so that means there will be dreams, the next generation astronomers, physicists, whoever will have, which cannot be fulfilled just because of that cost.
Right. Professor, my last question for today's program is, if you could communicate one key takeaway from your life's work to the world, what would it be?
It has been, and it continues to be so exciting. I'm blessed. Look, as I said, I'm 73. I'm supposed to be now being in the garden and planting little roses and stuff like that. Instead, I'm happily working, and I tell you, if I learn something new, I'm like children. Children. Like I have three grandchildren. When they experiment, just like they're doing things.
Right.
People are curious, and it's so exciting. It's so exciting.
Right. Professor, we'd like to wish you good luck, and we'd like you to stay a child with a lot of curiosity. And I'm really humbled that you made a time to be a part of my program. Thank you so much once again. I'm really honored for your presence.
Thank you, Sumit.
Thank you.
Bye.
Bye.